Thank you very much. Thank you, Vladimir. So I will now talk about smart assays for AOP-based mechanisms aware toxicity assessment. My name is Tobias Stoeger. I'm from the Helmholtz Zentrum in Munich, and I'm heading there a group which is doing research in particular on the respiratory toxicity of nanomaterials. So we are specifically interested in inflammatory responses in the lungs, in particular the alveolar region of the lungs, and inflammatory responses to sterile stimuli. So now here we will discuss about the smart assays that we aim to develop within our project to predict toxicity and pathway-specific toxicity with the awareness of the mechanism. I will use the already introduced AOP scheme from Sabina to guide us basically through this approach of smart assays, which always shall be linked to the respective AOP. And when thinking and looking at this 6 different pathologic outcome pathways, from fibrosis to lung cancer and lung emphysema, we realize that the molecular initiating event actually for 5 out of the 6 pathways shares the interaction with the cell membrane. So obviously, particle interaction or nanomaterial interaction with the cell membrane is a very central and crucial issue. There's only one AOP here, the AOP for acute lung inhalation toxicity, which does not require particle cell interactions, but is rather already induced upstream of that by interaction of nanomaterials with lung surfactants. And we will certainly hear more details about lung surfactants later in this session from Jesus, but I already want to introduce this AOP to you, and in particular this assay that is developed by Jurit in Denmark. So she uses a constrained drop subfractometer to test lung surfactant activity and its possibility to inhibit the surfactant activity, though the surface tension of the material under physiologically relevant condition by a particular mode of in vitro simulation. In this system, basically, she has a drop of liquid, of water covered with lung lining fluid, with surfactant film. And now if she adds hydrophobic or hydrophilic nanomaterials to the surface of the droplet, then this may interfere with the surface tension that the lung surfactant film possesses. And this can be then measured in this setup and be used as a readout for very initial phase basically of lung injury, namely a dysfunction of the lung surfactant caused by particle lung surfactant interactions. And she has done that already for a bunch of different materials, from quartz over several carbon particles, titanium oxide, and zinc and iron, and kind of by that ranked the ability of these materials to impair and inhibit surfactant functionality. So this is therefore the first fully developed smart assay for acute inhalation toxicity that we have developed within our SmartNanoTox project. As I said, most of the AOPs require an initiating event where the material needs to interact with cells, though, interact with the cell membrane. And there, a very famous, prominent pathological interaction leads to the so-called frustrated phagocytosis, which is particularly described for asbestos fibers, where the material to be phagocytosed is exceeding the size of the cell and therefore can never be fully internalized, as nicely reviewed here in this paper from Ken Donaldson. So the aim here is now to have an in vitro assay for frustrated phagocytosis, and this is actually this has been done by our colleagues in France, here in particular the group around Olivier, and it obviously turned out to be not so easy to really observe frustrated phagocytosis in vitro on cells, on macrophages, which are growing adherent to a surface, have a very flat shape, very actually specific shape, maybe not very natural. And what Olivier's group then identified is they might be able to use the macrophage fusion, so the formation of macrophage syncytia, as a response to frustrated phagocytosis, or at least the non-ability of completely phagocytosing particles, in particular fibers, in their lab. So this image here shows you a syncytia, or a fusion of several macrophage cells, a formation of a so-called multinucleate macrophage around, obviously, internalized carbon nanotubes, and you can see the carbon nanotubes here highlighted with the blue arrow on the plate in the microscopic image as well. So this has so far been established for the NM401, a rather rigid and long carbon nanotube, and this needs to be broadened out now for different and more nanomaterials to see how applicable this setup is to really predict frustrated phagocytosis. Another very important key event there during frustrated phagocytosis, or at least on a more organelle level, is the damage of the lysosome by phagocytosed materials. Though also there, once the material is exceeding the size of the lysosome can be damaged, but also specific surface functionalizations of the material might impair lysosomal integrity. And one famous assay to observe lysosomal destabilization is the quantification of cathepsin B, a lysosomal enzyme, in the cytoplasm. So the release of cathepsin B into the cytoplasm is a key event that will cause a stimulation, an inflammatory and even apoptotic stimulation of the cell. And Olivier with his group is here measuring, quantifying cathepsin levels, cytoplasmatic cathepsin levels at different conditions. So the left control bar tells you about what is the maximal release, scale to 100%, and then a negative control with an inhibitor. The lysosome is absolutely protected, and then different kind of exposures to different nanomaterials, and they detected that particularly amino-modified carbon nanotubes are very potent to permeabilize the lysosomal membrane, so they are toxic for this particular particle-cell interaction pathway. Then more downstream of the lysosomal disintegration would be a inflammatory, or as I said, maybe also apoptotic stimulation of the cells. So an inflammatory stimulation of alveolar macrophages exposed to different carbon nanotubes has been investigated here by Olivier, where they looked into the release of different cytokines and inflammatory mediators into the medium of the culture, and relating that to control levels set to 1, you can see that at least up to a 3-fold increase can be detected in this in vitro system. And further investigations need to tell how predictive this will be for the in vivo responses we know from our studies in mice and rats. So, as I said, and as you probably all know already, the increased secretion of pro-inflammatory mediators here at the very beginning of the key events is crucial and is very, very relevant for most of the AOPs we are interested here. Now, for that, of course, one would like to have a in vitro system where the inflammatory response in the alveolus can be quantified, can be mimicked, and therefore the inflammatory potency of the material can be predicted on the in vitro level. So we, with my group, we have been working on that since many years for particular carbon black-like materials, and I can tell that this is actually a quite difficult task. Even if carbon black, we use Printex 90 mainly, is producing a very robust inflammatory response in the lungs of mice upon inhalation or instillation. We failed to see any inflammatory stimulation of alveolar epithelial cells or alveolar macrophages exposed to Printex particles, but also exposed to other materials which are listed here. And we looked for several genes and the release of the classical neutrophilic chemoattractants or other major inflammatory markers like TNF, IL-1 and IL-33. But it's obviously not so easy to detect an inflammatory stimulation at the in vitro level. Also using bone marrow-derived macrophages from mice to just have also a different population of macrophages in the system, and doing genomics with that after 3, 9, and 24 hours did not give us any inflammatory signature for Printex 90, and also a very moderate one for double-walled carbon nanotubes, not really to be clearly called an inflammatory signature. So this is very surprising and astonishing at one side, because we are able to observe particle cell interactions, we are able to detect ROS release from those cells, and we are able to detect MAP kinase signaling after particle cell interactions very early, 30 minutes after treatment already. But this obviously does not lead to a transcriptional response. So to understand which cell type actually in the lung should be used for this inflammatory, pro-inflammatory mediator release in vitro assays, we started to do a single cell sequencing experiment together with colleagues from our institute, from the group of Herbert Schiller, who is a real expert in single cell analysis, in particular of lung cells. And then from these different populations of cells that we kind of isolate and that we sequence each individual cell and then map it to this cell populations, we recover a pattern of gene expression that we hope to learn which genes are the first to be induced and which are later on then more related to the pathological outcome after 6 or 28 days of exposure. And we did that for various different nanomaterials and also LTSS positive control. Now, just to give you a view on that, showing you a matrix plot, a kind of heat map where you see the most significant inductions of here a panel of different acute phase genes and the particular cell types where you see these genes to be induced. And then this is now a summary of all the different treatments. You can appreciate that actually not only the macrophages and alveolar cells actually, but also bronchial epithelial cells, and then in particular fibroblasts seem to be important sensors of the particle cell interaction, and then probably driving and maybe even initiating an acute phase response in the lungs. So while this was quite surprising and unexpected for us to observe this role for fibroblasts, actually, it's certainly important to realize this for the plaque progression AOP, where we are interested in the release of serum amyloid 3 from lung cells and how this then actually contributes to systemic responses such as form cell activation. And it's interesting to see that SAA3 is induced in fibroblasts here by Printex, but then at a later time point, even more by Mitsui, by the the carcinogenic carbon nanotube fibers, and a very similar pattern is observed for TIMP1, another very co-expressed, very well-known co-expressed gene to SAA3. Okay, now looking more into the epithelial signature and which cytokines actually might be triggering the inflammatory response in neutrophilia that we most often use as a readout for pulmonary toxicity. We observed here that the classical neutrophil recruitedly after Printex 90 stimulation from alveolar epithelial type 2 cells, and this is actually very well matching the kinetics of this response, is very well matching also the kinetics of the neutrophil accumulation in the lungs. This is also very well matching our previously published idea that not the alveolar macrophages, but rather the alveolar epithelial cells kick off the inflammatory response related to Printex to carbon black, so not carbon nanotube, but carbon black particle exposure. Another AOP that we are very much interested here in the consortium is driven by Hendrik Wulff, and it's about the TFF2, IL-33, Th2 axis of fibrosis, introduced already by Sabina this morning. So there we are, of course, interested in the cellular source for TFF2 and IL-33 and Th2 cytokines, and using the single cell data, we observed that the cellular source, obviously, for TFF2 should be the goblet cell, the club cells, for IL-33 later, then 82 cells, and for the Th2 cytokine, the important one, the eosinophilic cytokine CCL11, the source is obviously from the fibroblast. So it seems that the more proximal region of the distal end of the lung, so maybe close to the athenos, so where we have goblet cells and where we have club cells in proximity to 82 cells, this might be a very important point of interactions for fibers. So then finally, actually talk which should have been given by Georgios this morning, but he couldn't do it. I will just briefly touch on it. So therefore, the lung cancer AOP, of course, a very, very crucial key event is the increased detection of DNA damage and DNA mutations in structural lung cells, less in in leukocytes, but more relevant in structural lung cells, so as lung epithelial cells. And so we did this here. This was basically actually performed in the group from Georgios Staphopoulos at our institute, a real expert in molecular lung carcinogenesis. And what they did is that they exposed cells, mouse and human alveolar epithelial cells, to different carcinogens, but also to Printex and Mitsui particles for 24 hours, and then washed the cells, removed the particles, and cultured the cells by changing the medium and so on, and for another 8 days. So for 1 week after exposure, basically. And after that, the cells are then analyzed by deep sequencing, by RNA sequencing, actually, to detect coding mutations, so mutations in coding regions of genes. And when doing that, we could see that actually Mitsui and Printex cause a quite significant pattern of mutations in murine lung epithelial cells, as well as in human bronchial epithelial cells. And when you look here, the quality of the mutations, or whether it's deletions, insertions, or just single nucleotide variants, really depends on the material, and it also depends on the cell. And it was quite astonishing to see that Printex seems to be very potent in producing insertion mutations, but also deletions. And then you can, of course, also look into the single nucleotide polymorphisms, what they mean, what kind of transitions or conversions are happening, and what the flanking sequencing actually, how those give a particular pattern of mutation. Then this will be further analyzed, but I would say that this so far looks very promising as a new in vitro approach for testing the mutagenicity of new materials. And with that, I would just like to conclude with a summary of the different smart assays that SmartNanoTox is working on. The two blue ones are quite finalized. The more black ones are in progress, and some of the more gray highlighted assays seem not to be at least possible in the kind of in vitro systems that we have used so far for detection of these key events. With that, I would like to thank you all for your attention, in particular my group in Munich, of course, collaboration with Ottmar Schmid, very important, and of course, great thanks to all of the entire SmartNanoTox team. Thank you very much.